I'm Pat Malone. I'm Professor Emeritus of American Studies and Urban Studies at Brown University. I specialize in industrial archaeology. Today I'm going to be talking about the first iron water wheel in America. In 1813, the state of Massachusetts chartered Francis Cabot Lowell's Boston Manufacturing Company, or BMC, which set out to put all the preparation, spinning, and power weaving processes in the same mill, a significant change from previous textile mills in Britain or America. The upper red circle locates Waltham, a town on the Charles River 9 miles northwest of Boston, that Lowell and Patrick Tracy Jackson chose for their first mill. The river had enough potential drop at the upper of 2 mill privileges there. But since 1639, a significant part of its flow had been diverted into Mother Brook at the lower red circle, and from there to the Neponset River. Here's the dam in Waltham with the first Boston Manufacturing Company mill, now enlarged. Lowell and Jackson moved quickly, not only buying the boys' paper mill property in 1813, but also raising its existing dam to give 12 feet of head. By 1817, there were 2 mills in a line, fed by the same power canal. My Brown student, John Peterson, created this model of mills number 1 and 2 for the Charles River Museum of Industry. The real mills were in the distance with a connection and additions. The large pond that could be drawn down several feet was a significant asset, but there had to be enough flow to refill it at night. In 1831, the BMC agent complained about, quote, the failure of water in seasons of drought. The uncertainty of the water power on Charles River is, as you are well aware, a serious evil, unquote. Floods and winter ice blockages were also major problems. The 13-foot diameter wheel, old but still operational at the Lowell machine shop, is shown in this image. It was similar to the 12-foot wheels at Waltham. All had efficiencies of about 60%. Like most wheels of that period in New England textile mills, this one was primarily wood, with 40 buckets and an iron axle. It was a high breast wheel because that form, with a close-fitting breast or apron, worked better than overshot wheels in backwater and could handle varying levels in a mill pond. Note the external rim gear of this wheel. High machinery speeds made it advantageous to mesh a small spur gear with a large rim gear for maximum increase in RPM. The Gillette grist mill in New Hartford, Connecticut, had a high breast wheel with a rim gear. SIA members recorded this circa 1850 wheel for the Slater Mill Historic Site as part of the design process for the museum's wheel recreation in its Wilkinson Mill. During excavations at the Wilkinson Mill, we concluded that its 1821 mid-breast wheel also had an iron axle and an internal rim gear cast in segments. Chuck Parrott and I designed the Wilkinson wheel, which was built by Walt Pulaski, Joe Moran, and Mickey Jadach. Its iron cruciform axle was based on drawings in Lowell. One of those drawings was of an iron water wheel. We found this sketch of an iron water wheel many years ago in the Locks and Canals collection at UMass Lowell. It was drawn by or under the direction of engineer James B. Francis in 1844. After being asked to design iron water wheels for the new Prescott Mill in Lowell, Francis went to see an early example in Waltham. The text on the measured drawing is very specific. Sketch of a water wheel at Waltham, imported from England in 1821. Wrought iron buckets, 1/4 inch in thickness, 18 feet long. There are 36 buckets. The surrounding in the center is listed as 1 inch thick cast iron, and that's shown on the right sketch. The drawn wheel is 12 feet in diameter and has a cruciform cast iron axle 21 feet long. This breast wheel matches the 12-foot diameter of wheels at the main BMC site on the upper of Two Drops in Waltham. It's also almost exactly the same width. Because it was iron, the Boston Manufacturing Company could expect it to last much longer than the usual 5 to 10 year life of wooden wheels. Despite its innovative use of iron, the wheel is still a relatively conservative form with 6 heavy arms. This cropped and clean view shows details of the wheel in cross sections. Arms that are that heavy were really unnecessary since there was a rim gear. Power was taken off by a spur gear at the rim instead of being transmitted through the arms and axle to a separate pit gear. Although no rim gear is shown, there's not enough room on the axle for a pit gear outside the wheel. Terry Reynolds from Michigan Tech supplied key evidence after I showed him the drawing of the 1821 Waltham wheel. He said that the noted British wheel designer Thomas C. Hughes testified in an 1824 parliamentary hearing that he had exported an iron water wheel to America. Terry also pointed to James Dunlop, a British observer who reported that he saw a Manchester iron wheel while visiting American textile mills in the 1820s. I believe that the Waltham wheel drawn by Francis was the one exported by Hughes and seen by Dunlop. Until recently, I assumed that the wheel went to the main BMC site at the Upper Privilege. But before we look more closely at Waltham, let's investigate the British development of iron water wheels. Here's an iron axle from an 1820 wheel at Quarrybank Mill in Style, England. This mill is often credited with installing the first iron water wheel in 1807. Hughes may have built that wheel at his Manchester machinery plant, although it was installed by millwright Peter Ewart. Hughes definitely advised on wheel repairs and improvements in 1815, and he apparently put in a very large breast wheel, 32 feet in diameter and 21 feet wide in 1820. That great wheel ran until 1904. Its cruciform cast iron axle resembles the somewhat shorter one that Francis drew at Waltham. Hughes made this wheel for a mill in Belper, England. The great wheel at Style was a suspension wheel, the innovative form developed by Hughes and first used at Belper by 1811. Working for the struts, Hughes built a pair of wheels in which he used thin wrought iron rods instead of traditional heavy arms. Each wheel was 21.5 feet in diameter and 15 feet wide. With power drawn off by rim gears, there was no need to transmit it through the arms and along the axles. Radial rods in tension could hold the rims in perfect circular form, as we see in modern bicycle wheels. Additional diagonal rods running from the hubs to the center shrouding braced each wheel. This was an iron wheel except for its wooden radial floats. This drawing and a detailed description of the wheels appeared in Abraham Rees's Cyclopedia by 1820. Francis Cabot Lowell may have seen the actual wheels in Belper during his investigations of British textile mills in 1811 and 1812. Industrial espionage was his specialty. He borrowed the idea of a water wheel governor after seeing an example in Britain, and Belper had one of the first of these speed regulators. We know that he planned to visit Manchester, where Hughes had a large shop. Lowell died in 1817, but copies of Rees's Cyclopedia would have been available in Waltham or Boston before 1821. The BMC was at that time the most prosperous and creative textile firm in America. Its leaders were deeply interested in British technology. There's a Hughes suspension wheel in the Royal Scottish Museum. This slide, purchased from the museum, shows, quote, Hughes and Wren, Manchester, 1826, cast into the shrouding of an iron wheel 25 feet in diameter and 22 feet wide. but in this case with wooden buckets instead of radial floats. Curved wrought iron buckets of the type used in the Waltham wheel were a more efficient alternative, but harder to replace or repair. Wooden patterns for iron wheel parts survive at Finch Brothers Foundry in Sticklepath, England. Shrouding made up of cast iron cants like these could be designed to support either wood or iron buckets. These patterns fit two sizes of overshot wheels at the foundry. One wheel has wooden elbow buckets, while the other has straight float boards. The Middleton Distillery in Ireland installed an English wheel in 1852. Sir William Fairbairn was a Scottish engineer who worked for Hughes in 1816 and 1817, and later praised him for developing the suspension wheel. Fairbairn went on to build many iron wheels, like this one 22 foot in diameter, that he sold to a maker of Irish whiskey. His highly efficient buckets of curved wrought iron were ventilated to avoid trapping air and to ease the discharge of water. Let's go back to Waltham to see where I believe Hughes sent an iron wheel in 1821. This circa 1877 bird's eye view from the Leventhal Map Center shows the upper and lower privileges after much expansion and the addition of steam power. By raising the existing dam, which is here, in 1813, the BMC created an expanded mill pond. But the elevation of the pond and thus its storage capacity was limited by prohibitions against creating backwater for mills upstream in Newton. Backwater, or water rising into wheel pits, adversely affected the rotation of vertical water wheels and sharply reduced their efficiency. It was an occasional problem on any river during freshets, but was a major concern if a dam downstream from a mill was high enough to create frequent or constant backwater. As the BMC was putting its first mill in operation, the breast wheel suffered from backwater caused by the Waltham cotton and woolen factory just downstream, which is up at the upper right. The factory apparently raised its own dam while Francis Cabot Lowell was raising his. The Boston Manufacturing Company sued over backwater and won in 1816. The court ordered the factory's dam lowered 18 inches. By the date of this bird's eye, mills 1 and 2 were connected and additional buildings were in place at the upper site. Even with BMC's use of more efficient water turbines, the river was still an unreliable source of power. The big improvements came with steam power as a supplement for water power in some operations and as the sole power source for others. The BMC installed its first steam engine in 1831 and did a major study of steam power in 1836. Hybrid power systems using both steam and water had great advantages for textile mills. In 1819, the BMC bought the downstream mill privilege of the Waltham, Boston, and Woolen factory. This 1877 view shows the site's later use, primarily for bleaching, dyeing, and some knitting. The first experiments with steam power by BMC were here. Steam exhausted from engines had great value for hot processes. The BMC sold more stock in 1820 to finance building a third mill. Business records make it clear that mill number 3 was at the lower dam, where the company went on to develop its new bleachery and dye works while tearing down the earlier wooden mill. Capital expenditures in BMC business records from 1821 through 1822 are almost entirely for mill number 3 and its machinery. The small mill of 2,000 spindles was unusually costly. The valuation for mills 1 and 2 at the upper dam does not increase enough to suggest the replacement of a wheel in either of those mills. The expensive iron wheel surely went to mill number 3 at the lower site. This historic photograph of the bleachery complex shows mill number 3. My grad student, Kristen Peterson, included this photo from the Waltham Historical Society in her book, Waltham Rediscovered. Notice how the mill looks like mill number 1 at the upper dam. The photograph complements this drawing of the bleachery at Waltham from Gleason's pictorial in 1853. Because the BMC was secretive about its pioneering textile chemistry, few visitors would have seen the iron wheel at this site. An 1874 Barlow perspective from the American Textile History Museum, in a collection now at the University of Southern Maine, shows the mill, by then numbered 15. The cupola is gone, as you can see. The accompanying Barlow site map shows the race still in place, and the race is over here. It was probably used just for processing and boiler feed water by that point. Steam boilers and engines are prominent. Was the wheel retired but still there in the 1840s when Francis drew it? Or was it still in use? Maybe BMC millwrights had moved it to the upper site when they made improvements there. Records from the early 1830s show plans to shift the machinery in mill number 3 to the upper site, and even suggest selling part of the water power at the bleachery. The 12-foot diameter wheel could have worked as a high breast wheel on the upper dam. It must have run with less head on the lower dam, probably around 8 feet. Decades later, the old mill is shown as a hosiery manufacturer, number 15, but still making fabric of a different type. I think the wheel was still in place at the bleachery in 1844, but a steam engine could have supplemented or replaced its power before Francis's visit. The BMC spun off the Waltham Bleachery and Dye Works as a separate company in the early 20th century. In recent years, any surviving buildings were destroyed to create a shopping center, but the raceway entrance survives. The dam has been lowered significantly, probably to increase the head at the upper privilege. No signs explain the history of the site. There's no evidence of any iron water wheel in America before 1821. Jacob Perkins built a high breast wheel with iron buckets and a perimeter gear at Amesbury in 1796, but most of that wheel was made of oak. So far, I have found no specific documentation of the imported iron water wheel at Waltham other than the drawing by James B. Francis. His construction drawings for the Prescott mills in 1844 indicate that he borrowed details from the 1821 wheel. The Prescott mills put his new wheels to use, but the corporation folded almost immediately and was absorbed by the Massachusetts mills. By then, water turbines were a much better choice for most manufacturing. Thank you.